My name is Hans de Nivelle, and I'm honored that I'm invited or was allowed to speak at this conference. And I'm going to speak about C++-based parser generation. And I developed a tool, maybe a library, or it is a bit like a tool, like a library, which is called Maphoon. I will speak about this, but I will also speak generally about parsing. And moreover, so something maybe general. So I have been teaching compiler construction many times, and in these compiler construction courses, it's nice to have a parser generation because we teach the theory, but I found out that there is no good one for C++. So we use sometimes Java. In Java, there is a tool which is called Cup. So it has to do with the coffee, of course, but I think it means construction of useful parsers. And it's a really nice tool, and for C++ there's no such tool. I mean, that's what I observe all the time. So there was something called the famous Yak and Bison, and they are C-based. And of course, C is in a sense a subset of C++, but when you do this, you're not using the features of C++. Especially, you are not using, or the RAI, how do you pronounce this? I mean, you cannot have classes that have destructors and copy overload, because if you use Bison, it will just not happen. You have to do the memory management by yourself, and C++ has all of this semi-automatic, and you want to use that. So that was my initial plan was just to rewrite. That was one thing, and another thing, but I will come about, is that I'm currently implementing a programming language in C++, and I just need such a tool. And again, I looked at the existing ones, and they all have something that makes them not usable. And I mean, I will not list them all, but I will somewhat hint at what are the problems that I encountered. And I think, so if you if you use an automatic tool, it gives you a canned solution, and usually this canned solution is not exactly what you want, and because of this, I think many people refrain in the end from using tools. But I try to find the right combination between flexibility and automation, and that's very important, especially when with tokenizing. I will come to that. So that's for the moment. I will also try to have some real content. So let's start at the beginning. How do we pronounce Maphoon? I prefer to say Maphoon, and not, people like to say Maphoon, but that's not how I think it should be pronounced. Maphoon. It doesn't rhyme with lagoon. And yes, so that's not important. But I will be honored anyway, however you wish to pronounce it, but like this. Okay, let me say shortly where I come from. So I work currently in Kazakhstan. I'm actually Dutch, but I work at Nazarbayev University in Kazakhstan. That's far away. And actually the time from there is completely reversed from here, and we are still suffering from this. I'm still, I think bigger jet lag is impossible. It's as far apart as the keys of C and D flat. It cannot be more so. Okay, so the current state of Kazakhstan exists in 1991. We just celebrated independence a couple of months ago from Soviet Union. So it has approximately 19 million inhabitants, which is, I mean, in terms of population, not so big. But the surface area is incredibly big. So it's 2 million square kilometers. And so a million square miles. Sorry for using an SI unit in the US. So Kazakhstan is very rich in natural resources, in oil and gas and all kinds of things, copper and iron and rare metals. But and this is usually bad. But compared to the neighbors of Kazakhstan, the government is really using these riches and investing it in the country. And that is nice. So and so my university is a consequence of this. Maybe yes. So my university is where I currently work is called Nazarbayev University. It was founded in 2010. I think there has been a somewhat half successful attempt before it, but the current incarnation is from 2010. Before that, there was a program to send the best students abroad, but this is now terminated. We now keep our best students and educate them by ourselves. So it's about a big 4,000 undergraduate students, 1,500 graduate, 700 students in something called foundational year. The language is English, So in this foundational year, people study maths and English, and if you don't pass this course, then you are not going to make it to the second years. So the language there is English, and everyone speaks English. So, and I believe that in the computer science, the department is looking for, well, I'm sure they're looking for people. And so there is a chance. So everyone is required to live on campus, especially the students, in order to reduce social inequality. And all the important decisions that involve anyone are based on merit only. And really some of the decisions, they're made abroad, so we send the exam results abroad and make sure that they're evaluated in the UK, so that there is really no way that something could go wrong. So I work at something called School Engineering Digital Sciences. It's also quite big. I think it's the biggest school, and the computer science department is the biggest department in terms of students. So especially because of that, we are very much looking for professors. Okay, something about C++. I learned C++. I learned C at university in 1986, I believe, which was a bit of an underground activity because the teaching was based on Pascal, but I like C much more. Then I learned, so then all the time, I think for a period of maybe 7 or 8 years, I was all the time asking colleagues, should I learn C++, should I learn C++? And they always tell, no, you don't need to learn this because we now have Java. And C++ is going, efficiency doesn't matter anymore. C++ is low level, forget about it, skip that. But so I think I, in the end, learned it in 2002 and I liked it. And yes, and then I have been teaching quite long C++ in Wrocław University in Poland. And I now teach it in Kazakhstan also, but not as a standalone language. We use it in the data structures course. And yes, 2 days ago, what was his name? Amir something Kirsch, he spoke about teaching C++. And he thinks it's not really good that it's not taught independently, and I agree with him. Because students miss some of the important language constructs because of this, because of the fact that we're only using it and not really, going in depth through it. And I use it very much for implementation of logic. We will come to this. Okay. So, I'll say something about my relationship with compiler construction. There is a Dutch saying, who can does and who cannot teaches. So I taught compiler construction in Wrocław a couple of times. I taught it in Nur Sultan also, and I'm going to teach it probably in the next semester. But currently I have a grant in which I am developing and implementing a programming logic for logic, and for this. And this has to be implemented in C++, and this is also again why I need these parser generation tools. I just develop it because I need it. And this goes back to this. So, and I hope I'm not saying something terrible, but C++ is not so suitable for implementation of logic, and I do not know. I cannot get my finger on where is the weak point. I would like to, but I cannot find it. So if you have this, so. Yes, okay, so I say this here, logic is somewhat special because you have trees. So trees can be easily implemented in C++, but these trees are very heterogeneous. So you have, trees, every node has a different type, and you need to all the time cast this or check what type the subtrees have, establish their existence, and the code is always ugly. I do not know, and I somewhat want to try to find a type system based on tree automata that would deal with that. So in the end, I say here it's about taming the union. So this is if you have C++, how is union implemented? You have union, you have variant, you have inheritance, you have tricks with null pointers. Sometimes people use how is it called stdod, the max int, and the trickery is infinite, and we don't know yet how to deal with union. This is what I think the root cause. But let's now get to the real thing. Is this important? I give you a short example of what I want with my language. So this is first order logic. But we come to parsing in a few minutes. So this is, you have terms, right, which is just a tree. This is the top node, these are the subtrees. And then you have all kinds of logical operators which construct formulas. So one is unary, one is you have infinite, how you call n-ary, and you have exactly strictly binary. And then you have quantifiers which take a variable and and another formula. Oh yeah, and this one takes terms, and these terms are here. So here you see these different subtypes. Some of them are terms, sometimes they're also formulas, sometimes they are variables. You have this restriction. So, and I want to be able to, if you look at this definition, try to use your photographic memory. I want to define it like this in the language. So for is a struct which has a selector which tells the type, and then here you just define the subtypes. Right, so if you have an AND or an OR, you have an unbounded number of subformulas which are also full. If you have implies or if you have two subformulas which are both full. And if you have a quantifier, you have one variable. You have an unbounded set of variables, and you have one type. Oh, you have types also. They were not in the definition. Sorry for that. So this would introduce another subtype, and then you have the body, which is again a formula. So I don't think there exist other languages where you can write this on one slide. And this I want to parse in the end. And let's say something about this. So this is ultimately what I'm developing this. Have been developing this for. So I have been using this. So I want things that are as nice as this cup and this JFlex. This is Java. I think F, I don't remember what it means. This is the well-known Lexer tool. Okay, this is CUP. This is, how to say it, construction of useful parsers. Okay. Yeah, and then, okay, so who are the user group, the intended users? Of course, first of all, myself, but also, big established languages like C or C++ probably don't need parser generators because, the compiler is so big that the time invested in constructing the parser is not that much compared to the total complexity of the project. And also the syntax doesn't change. The syntax of C++, when did it change for the last time? I don't remember. Okay. And for experimental languages, they're very useful. I'm changing syntax all the time, and you just do it, and 1 hour later you have another syntax. Or 2 hours. That's useful. So I decided I looked at existing ones, and they all have something that makes them not suitable for my project, and I will come to that. So I decided to. I'm also a little bit afraid that in the end nobody will care about my programming language, and I thought if I construct a compiler tool, then at least something useful will come out of this project. Then that's what I thought. So now, okay, yeah. Okay, there are the talks by, what's her name, Hanna Drisikova. And, but this is different. This is a different application of regular expressions. So if you do it for pattern matching, then you use them in another way than when you use them in compiler construction. So this is, if you use them for pattern matching, you match and then you decompose something in components, and that's not really what I'm doing. So this is quite different. The goals are different. I just wanted to mention that. So now we come really to parsing. So what is parsing? So in computer science, nearly everything is a tree. We know that in theoretical computer science. But the input comes as a stream of characters. So the task of the parser is just to extract the tree structure out of the stream of characters. One could say it like this. And the resulting tree is then called abstract syntax tree. And once you have the abstract syntax tree, you can do further things with it. You can do type checking and further compilation or whatever you want to do with it. Okay. So this is just an example of an AST. You have this little program that makes that something is uppercase and you make it lowercase. So if the letter is between A and C, you subtract the capitality and you put like the lowercaseness in place of it. Right, this is what it is. And this is a comment which will be completely ignored by the parser. So with the end you have an if with an and. This is this and. This is actually an expression. I omitted the type information. And this is a statement. So here you have this plus is the variable and this minus and some character constants at the bottom. So the parser would read this and construct something like this, which is AST. And then if you want to compile this, you have to attach type information, decide what is L or R value, and possibly invert conversions, and then you can produce code from that. Okay, tokenizing. So usually, I mean, I think nearly always, but not always, tokenizing is done in, parsing is done in 2 steps. So first is you go just through the stream of characters and you cut it somehow into pieces, which are called tokens. And so typical tokens are the numbers, which can be integer or floating point. You can have strings. Actually, strings are very complicated to parse, because character constants, I mean, because you have all these escape codes and whatever. Then you have reserved words, you have operators, you have comments, and sometimes indentation changes are tokens. So in Python, they would be considered tokens. Right? Python uses obligatory indentation, and if you change the indentation, the parser needs to know about that, and then the tokenizer generates a token from that. That's so. That is yes. That is tokenizing. So here, right, when here the if would be a keyword. This parenthesis is a token. I mean, this space then is a token which will be ignored. Variable is a token. The greater equal is token. The character constant. And this is also, I mean, for the tokenizer, it's a token, but it will be thrown away. The parser will never see this comment, of course. Never see this comment. So, okay. This I said so now. Okay. Okay, now, there exists a very nice theory for generating tokens and recognizing them, which is you just define them as regular expressions. You make automata from the non-deterministic automaton. You make this automaton deterministic by the subset construction, and you minimize this automaton. Right? This is what. So, and there exist nice tools that implement this. So flex, JFlex, re to C, regular expression to C. So why did I not use an existing one? Okay, and the problem is this. And here is something. The problem is the lack of flexibility. So if you use for all of them, there is something that doesn't fit into the system. So these systems they give you a complete tokenizer, but then there is something that doesn't fit in. This I mean, my language uses Python style indentation, and this doesn't fit in because these tools on the previous page are not able to generate that. And then I want to have comments of this form, which is intended for switching off code. So you switch off a code block, and here it switch on again. But these things can be nested. Yes, and as soon as they are nested, they are not regular, and not regular means that finite automata cannot recognize it. So and then long comments of this form, you typically don't want to put them in the buffer because they are long and they're irrelevant. So you would like to deal with them separately, perhaps. Right. So this is yes, and some languages whose name I will not mention have a quite intricate mixture between types and tokenizing, and the tokenizer needs to know what are type names, because they will be different kind of tokens. And then there are even languages that have certain tokens that are allowed only in certain contexts, like this one. This was an addition in C++11 that you can write and the template nested template definition with such a token. Which, right. Again, so I will not. I think I betrayed the name, but I'm not mentioning. I betrayed the name. Okay. So, and I hesitated quite long if it's worth implementing tokenizing, but I did it in the end. But I kept these goals in mind. So flexibility. It must be possible to handle some tokens by hand. So that's really important. You saw why? Because if you cannot, then so if you. So yes, and also the tokenizer must not dictate how source information is handled. That's important. So if you cannot use a tool that, I think in general, people tend not to use tokenizer tools even when the theory is nice. And I think it has to do with the lack of flexibility. Right? There's always something that doesn't fit in, and you want it, and then it kind of disqualifies the tool. So, and it has to be, this was not a goal, it has to be usable in education. I'm a university professor, and I want to show the automata to the students, just that students know what is happening. So what I do is I provide the building blocks for the tokenizer, but not the tokenizer itself. That's my solution. And on the next slide, I will start. The main building, the first building block is something called a file reader, which is just an interface, a simple interface between the input and the input file, the input source, and the tokenizer. And since the tokenizer generator does not generate the complete tokenizer, the user will have to interact with this class. So I quickly show how it works. What it is. So it's a very simple class. So it in the end contains a pointer to a file, but you don't need to know that. I wish that you could become owner of a file, but you cannot in C++. So yeah, and it does keep track of line number and column position. But these are the main methods. So it has a method has, which checks that it has n tokens in the future available and puts them in the buffer. So if it returns true, then you know that there are n tokens. If it cannot get n tokens out of the file, not tokens, characters, sorry. If it cannot get n tokens out of the character, it will return false. And then you should also not further try to get these tokens. Then you can get the i's character from the buffer, but I must be smaller than your last call to n, of course. Then you can get a string view from it, which just gets up to the i's token, the buffer as a string view. And you can commit to the i's to the i's character, which just means that you throw away everything before I. It does then. So if you have n tokens in the buffer, n must be certainly greater or equal to I. Then after that you will have n minus I left. So. Now this is simple, but it's somewhat. I think it gives somehow the nicest interface after trying. So, oh yeah, and this is important. So for every token that you want to recognize by hand, you have to write something of this form. So you take the file reader and you return a pair consisting of the type that you recognized and its length. So it doesn't for the rest do anything. So these are the main recognition function. And if you cannot recognize the function that you must recognize, then the second component should be 0. And that's because then you did. There's no empty token. And in principle, you can also recognize many tokens in one function. So if you say have integer or double, of course you could write the function try number, which then in its first component will tell if it was integer or double. Okay. Oh, it's shown here. I get all the time out of Parser. It's really you feel the altitude. Okay. So here is a very simple. This is really a very simple application. Where you where you recognize an identifier by hand. So try identifier. You first check. You must ensure that there is at least one token in the input. Then, if this is something that, the peak 0 is something that could start an identifier. So if not, then we are done. Then we have. But this doesn't. Then we have 0 length. Otherwise, we set then I to 1, and we check about the next character, if it could be something that continues an identifier. So plus I, and this goes. So and as long as that's the case, you increase I by 1, and then you return this I as a sim ident. So this is very simple. This is very simple code, and it's not really a good example because this token can be easily done automatically. But I took it because it fits on one slide. Let's say, but this is how you interact with the file reader, and I think somehow it's the nicest interface. I tried a couple of incarnations, and this is the one that I and also my students seem to like. Okay, now we come, of course, to automatic recognition. If you have, say, 20 or 30 tokens, you don't want to write 30 of such functions. So here I'm going to use a finite automaton. Here comes also some trickery. So you need to write. So again, I give the building blocks, but not a complete tokenizer. So you will need to write one function that builds something called a classifier, which is from my Lexing library. Okay. It's actually a template. You can specify the character class, but until now it has been always character for me. And you specify the symbol type, so that's an enumeration type. But say when you're teaching, it's also useful to put strings here that you don't have to put enumeration or whatever. But anyway, this is an automaton, and it's constructed by a function. It's called build classifier, but you can call it actually any way that you want. And it must be static, of course, because you don't want to recompute it every time you call this function. And there is something more to it, but I will come to this later. And it returns, it has the same interface as before. So then once you have it, you can call a function read and classify, which reads from the file reader. Yeah, using this automaton, it returns you this pair as before. It has the same interface as the function. So in the end, you get the function that has the same interface as before. It is this one. Yes, but you get it automatically. So okay. So now, the question is, how do you write this function? And now we're going to deal with automata, really. So this is an example of an automaton. So this is an automaton, right, that recognizes an identifier, but also the keyword while. So if you take while, you go this path, and the identifier goes this path. So you have any letter followed by a letter, and underscore followed by any sequence of letters or underscore. Yeah, and you see the problem with this automaton that if you have the word while could be also an identifier. So you need a kind of preference on this accepting states. So if you are in both, you need to prefer this one. Right, this is. And of course, this automaton is non-deterministic, because if you start with a double, you can be here, but you can also be here. So that is. So now that's automaton. So I use, I think, I have to show you some theory. So I use, which I think is a nice way of representing them, which also so a state of the automaton. No, the state is here, right? So these circles are the states. I have to start thinking a little bit about the time. So consists of three things. So we have a set of integers, which are the epsilon transitions. Okay, I forgot to tell something, maybe. This automaton. So if you construct this automaton automatically, you will not get such a nice automaton. It will be full of empty transitions, because the automaton are built and then combined. And it will be really full of epsilon transitions. It will be much bigger. So these epsilon transitions. So we have a set of integers which are just the epsilon transitions. Then you have this is the transition function. Okay, and I represent this by a step as something called a step function. So you have pairs of form character next state and in order to apply this, you must look for the biggest C prime that fits to your character. So you will see on the next slide an example. But so if you want to say that, say for digits, you go to a certain next state, then you have to say that from 0 you go to the next to some state, and then for the first non-digit, which would be the character after 9, you're not going to this state, so you have a blocking there. So the automaton, this transition functions represents intervals, but it makes the start and the beginning of an interval equal by storing only the points where something changes. So at the beginning of an interval, you specify where you're going, and then at the end of the interval, you specify that you can go nowhere from there on. And for this is the purpose of this hashtag. And then T is the classification that you would have if you would get stuck in this state. So and then the classifier is just a vector of states. Yes. And for the states, I always use how it's called relative addressing. So if you have a jump to another state, if it's the next state, the number will be 1. And if it's the previous state, the number will be -1. And if you circle in the same state, it will be 0. This is used in assembly language, and I also use it in the automata. So this is how I implement automata. So, and the advantage of this relative addressing is that you can very easily move or combine automata, and you don't need to do anything. You just put them behind each other, and the internal reference will stay right. Okay. And also the use of this step function simplifies the implementation quite a lot, because in the end your algorithms need to look only at the points where something changes. And this is convenient, I think. Okay. So this is an example from this is the same automaton as the previous one. So it recognizes while and identifiers. So and I think it's quite readable. So let's try to do it. So this is the first. This number here is not part of the automaton. It's just the index. So in the first state you have a lambda transition to 1, which is the next state, and to 4, and from 0 character on, which is the lowest character, you're blocked, and there is nothing else. So the first state has no real transition, but it has two epsilon transitions. Okay, so here we are recognizing the identifier. So from 0 onwards you are blocked, because 0 is not meaningful. But then from the capital A onwards we go to state 1. But then from Z plus 1 again. I mean, this is where so from A to Z you go to the next state. So 1 is actually the next state, because 1 plus 1 is 2. But then from Z plus 1 you're going nowhere until you meet the little A, and then you go again to 1 until you Z plus 1. And it seems I forgot the underscore. The underscore should also have been here. Okay. Oh no, the underscore comes only here. So and this is the circling state where you can recognize also digits. So from 0 you go to 0, which means circling. From 9 plus 1 you go nowhere, because then you're out of the interval. From A again you circle, and from Z plus 1 you again are blocked. This is the underscore, but the single character has to be represented as an interval. So from the underscore you go to 0, from underscore plus 1 again you're nowhere. And then, these are the digits. Okay, so, and this is then the part that, okay, this is the final state of this. This is from this circling state, you have also a transition to the final state. Which is, and in this final state you're blocked, but you can recognize the identifier there. Yes, and so before it you can, of course ident has to be has higher priority than error. Error always has the lowest priority, because you never want to recognize an error. Okay, thanks. And this is the while. So from W to W plus 1. You can go to the next state. All these ones are always to the next state, because it's all relative. Okay. So that's it. So and then so I will just show you some code, because it's easier. So I will show you how these identifiers are created using some real code, and also the classifier itself. So I will go to calculator class. Let's check what is the tokenizer. What is its state. I have to see in which state it actually is, because that's always a bit identifier. So okay, this identifier. So throw std runtime. Stop. Okay, let's deal with it. So this comes from a simple calculator. I will also use it later for the parsing. So, duck. So here you create the classifier. So this is the character type, is always character, and this is the types of the symbols that you want to recognize, which is kind of an enumeration type. It's defined somewhere else. It's not very important. And this is the default behavior. This is the default symbol that you recognize when you cannot recognize anything. So it's scan error. Okay, and these are like regular expressions. So range from A to Z, or range to big capital A to capital Z, that's a letter. And the digit is a range from 0 to 9. So this is different from other tokenizer generation tools that you define the tokens in code. So you see this here. And yeah, what the advantage of this is flexibility. So if you would, yeah, first of all, I don't like regular expression syntax. I like code much more. So I think, and secondly, it gives you the full flexibility. So I mean, if you have regular expression syntax, suppose that you want to repeat something like 20 times, then I mean, here I just write a for loop. And otherwise you would need some syntax for that in your regular expression syntax. It's much easier to do to provide the basic blocks and to do the rest in code. Okay. So actually there's never a regular expression constructed. So these operators immediately construct the automaton. So there's no representation of regular expressions. They're only automata. So, yeah, and this is the biggest one. Now, this is the comment starting with this, and then after that how to read this? So a comment. This is a comment starting with /star, then some let's say something that somebody finds important, and then /star \. Okay, so you start with this, then you have this start. And you can accept every character but not a star, or you have a star, a positive number of stars, but then it cannot be followed by this \. Yeah, and also not be followed by another star, and this you can repeat infinitely often. And then the exit is a couple of stars, and then just one single this thing, and then you're out of the comment. Okay. And this is the exponent of a floating point number. So it's e or e followed by a minus or a plus, which is actually optional. Okay, so this is a method of the automaton class. And then you have an optional digit. Then is this right or not? It looks a bit suspicious. Eh? Actually, this cannot be right. Do you think it's right? It's not right, because you can have a plus and then you can have no digits at all in this exponent. That is not right. So let's deal with that. I think one of them should be not optional, just so. Right, that's better. Okay. So. Yeah, and this is double. So into this classifier, you insert one classification. So if you have a positive number of digits, then optionally a decimal point and some digits after it, or an optional exponent, which we defined here, hopefully correct now. Then you recognize a double. This automaton doesn't distinguish between integer and double, so everything is double here. And otherwise you have to add some more cases to deal with the integers. This seems to be possible, at least in C++. You start with the dot, and then you have a positive number. Then you must, of course, have a positive number of digits, because otherwise you have a dot alone, which is and the optional exponent. This is the identifier. Which is so. This is the identifier here, so it's a letter, a digit, or just an underline. So it's not completely equal to the previous one. Oh no, it's the same. So you have a letter. It's the same as the automaton. You have a letter, or followed by a letter, digit, or just an underscore, an arbitrary number of times, and this is an ident. And then you have a couple of reserved words. So this is assignment, this is comma. You will see that we will later parse this also. Now we're only tokenizing, but later we will see the parser for this also. Okay. I wanted approximately to use half of the time for the automaton, so we must. So if I now run this, you will see the automaton. Let's do that. A calculator. No, why do we not see the automaton? Wait, something's going wrong here. CLS is. I think something bad is happening here. So this is why we're not seeing the automaton. Well, there it is. Is there a way to make this readable? Yes. Okay, this is surprising. So you see that this little automaton has surprisingly many states. So, this is the first one that I showed it just because we have like it's a concatenation of automaton for the separate tokens. And here you see the lambda, the epsilon transitions that branch into this different automata. And then I use the word blocked here instead of the hashtag. And then here we could try to read what is actually being recognized here. I mean, nothing useful happens here, or does something happen here or not? I think these are the white space characters. This is why you see nothing. This is the part of the automaton that recognizes white space. So I think there's a space that this looks like a tab. And this is somehow. And, but you should see that it recognizes white space. Eh? Where do you see this? It is here in the end, okay. Yes. But I will not now. But these automaton, if you look a bit, they're quite readable. But of course, in order to use them, you must make them deterministic. So let's do that. And surprisingly, it will have less states now. See the tokenizer dots. And we must also, I must speed up. Tokenizer. So you can make the thing deterministic. These are standard operations. Hopla, make tokenizer, the calculator. Yeah, so you mean what you see is that all these transitions are gone, all the epsilon transitions are gone, because so in this formalism, an automaton is deterministic if it has no epsilon transitions, which just means that these are all empty. Because this step function cannot be non-deterministic due to the way that it is defined. So this means that all the determinism has to be here. So if it's not here, then it's nowhere. It's not here. So okay, and then there's a standard. I think it's Myhill-Nierode construction where you try to merge states and see if that makes a difference. So. And before I was in the beginning too lazy to implement it because I thought, what does it matter to lose a few states? But in the end, it turns out that this minimalization removes really very many states. So remember this number. So remember the number. Okay, so we have 94 states. We minimize the thing now. So. Where did it go? And now we have calculator. And there's something that cannot be right. This cannot be right. Yeah, did this minimize? Oh yes, I see that. I should never show the deterministic automaton. I mean, I said that it was deterministic, but it was never deterministic. Wait, this makes no sense. So let's do it like this then for the moment. Tokenizer. Calculator. Yeah, so now we have 46 states. That's somewhat surprisingly the deterministic automaton is smaller, even though you theoretically have exponential blow up. But that's because of this incredible number of epsilon transitions that is introduced by the translation, by the construction. So 46 states, we're going to, now we do the minimization. Where is it? Yes, let's open that. This we don't need. So 26, so it's significant. It's not a thing that you can ignore. So it goes for, it's not half, but really very many states were removed just by this minimization. Then I will also show you the rest of the. So this is I showed this. So this I showed you. This I showed you. This I showed you. Okay, now we come to this part. So now I show you some of the parts of the complete tokenizer. I said, well, we cannot generate a complete tokenizer because then the flexibility would be lost. But I give you the components that make the tokenizer. So we come to the tokenizer. Read. So I think tokenizers are the only place in the world where GoTo is acceptable. Okay. So if the tokenizer does not even have a single character, that means that we reached end of file. So if the input is not good, then we have a bad character, a bad token. And here we call this function read and classify, which uses this static this automaton is constructed here. Of course, computing it is costly, so we put it in a static variable, and here it's used for read and classify. It returns this pair, as I said, and then you just look at the. I mean, in principle, you have to deal with the case that nothing was read. That is here. I suppose that will be a scan error. Okay, so in that case, when you read nothing, then you still need to try to advance one character because otherwise you will hang forever. So I try to, and we know there is at least one character because we checked it. So I just create a scan error with one character in it, so at least to move forward. And then you have all these things. You have white space and comments. So you commit to them and you go to the restart. So they are irrelevant. In principle, you could write a switch here if you want, but usually there are not that many tokens. But you need to deal with the tokens that have attributes and compute these attributes separately. Right? So if you have a scan error or an identifier, then you take the view of the attribute and you put it in the attribute. So in the end, you return a symbol with the type and the attribute. And the attribute comes from the string view from this file reader. I think the rest is not trivial. Okay. Now, does anyone have a question? Because you should have. Right? I mean, I spoke a little bit about efficiency, but what happens now in this code is that every time when you start this calculator, the automaton is constructed. And you would like somehow to store this automaton, of course. And here I use some very dirty trickery, which I really do not know how to do it better. So there is. So you want to keep this automaton, the minimalized deterministic one. So one thing is that you could do it in a table, but there is a nice paper from very long ago written by a name that I cannot pronounce. But there is a nice system which is called RE2C, so regular expression to C, and they studied different ways of implementing these tokenizers, and their conclusion is that you must generate the C code directly. And so you don't generate a table, but just generate C code directly. And I like that, so that's what I do. And now comes this is not yet the dirty part. Yeah, it's already. So I will just turn this on, then this will create a file. So what you do is you print the automaton that you just generated. You print it by a function called print code. And then this is compilable code. And then I later, you will see this, replace this function just by this automaton that I just generated. It's a bit dirty, I would say, but in that case, you completely skip the construction. And you get an automaton which, according to the makers of RE2C, is the most efficient possible. So I will turn off this if and show you what it actually generates. Let's go through the arguments. Okay, so this is the type of the token as text because it goes into it prints code. So you have to tell what actually is the type. So you have to tell it as text what is the type of the character. This is the type of the classification as text. Then this is the namespace, which we don't use. This is the file, this is the automaton. And these are lambdas that tell you how the character should be printed. That's important because in principle it's generic. That this can be any type of character. And there may be something that that is not trivially printable. So then you need to tell how it is printed, and that does this lambda do. So it says if the character is printed, it puts it between quotes, and if it's not printable, it prints it just as an integer. And what is this? And the same for the symbol type. You have to tell how it will be printed. And this is just we just put the string sim in front of it. Yeah, that's easy. So if you run it now, nothing will happen. I mean, I think. Oh, wacht even, it will throw this stop. I have to delete this stop. Otherwise, it never stops. So otherwise, it will never get to here. Calculator. So we just quit. Well, no, I think it must be done like this. How do you quit from here? I forgot really. I thought quit. Okay. So this is the automaton. So this is the automaton. So this is automatically generated code. So and it just has a. You see this here. It just encodes this. And it encodes this the transition function. So you see here the. So if you look at it, this is the same as the automaton that I just printed, but hard-coded in C++. I think this is not yet a truly dirty part, but it gets worse. And so do you see the characters? And now you want to use this automaton. So how do you do this? I provided an O. So if somebody could have a nicer way of doing this, I would be interested in hearing about this. Vi tokenizer.c++. So CLS is. So what I do is, I just turn off this one. It will not be called anymore. And now you do this. You just put a random integer here. So, and now this. And this automaton is included. You see this here. So it now. And now this function read and classify has an overload for integer, where CLS is not an automaton but an integer, and this will use this automaton. So that's so if I now run it, it will use the automaton instead of the construction. The C++ code. I mean, it is ugly, but so and. Yeah, I mean, and so now it uses the other automaton. So that is the hard-coded one. Why does it always go into these errors? So 3.14. Okay, quit. Yes. So that's. Yeah. So what is nice, I think, about this is that it offers you the whole trajectory from initially you just. It has a very low threshold to start using it, right? You just start construct the automaton, then you immediately can use it, and then later, so when you are certain that it is correct, you can do this other. You can really hard code the automaton and get the efficiency. But initially, you don't care about efficiency. You're just designing your language. So it has it doesn't have, say, a steep curve before you can start using it. You just start using it immediately, and then every time when you want a bit more, it gets a bit harder. And in the end, when you do the efficiency, you do this final trick, and then you ship your code, and you don't look at it anymore. Yeah, and I hope that you also see that you have the efficiency. So if you have a token that cannot be recognized by this automaton, you just insert it in this tokenizer. Okay, so I would say, do we have any questions? Because I'm going to the next stage, to parsing now. So this is about, this was tokenizing. I think it's fair to spend a bit more to tokenizing because it may be even more important than parsing in the end for many people. But I now want to move to parsing. So, no? That means how to say this questions. Okay. What shall I say? Yes. So we're now at the second stage, parsing. Parsing is done by something called formal grammar. which is also usually called a rewrite system. So, and we have a formal language course, and then we torment our students with this definition. So, a context-free grammar, this comes from a Sipser book. We used I forgot his first name, but we used the Sipser book. So, you have a quadruple where you have a set of non-terminal symbols phi, you have a set of terminal symbols sigma, and you have a set of rewrite rules of form one symbol. The non-terminal symbol can be replaced by a mixture of terminals and non-terminals. And we have a start symbol. So and then a word is in the language if you can start with this S and make replacement according to these rules, and then whatever word you can obtain, which consists only of sigma characters, is in the language. So that's the yes, and unfortunately this definition is not usable in practice. With the biggest problem, of course, is that with this definition is that it says nothing about meaning. Right? This always surprises students and me also still. That we say the language recognizes, but we never say what it means. And of course, if you are compiling, you care about meaning. So we're gonna do it a little bit different. We use something called attribute grammar. We still have a set of symbols, and we don't care anymore about terminals and non-terminals because I think it's completely unimportant. Okay, then to every of this sigma, you attach an attribute set. Yeah, and also mathematically a set is the same as a type, so it's just a type. So we just say for every symbol what we attach a type to it, and later a value of this type. So if we have the symbol, if we have say the symbol integer, then it comes with an integer, of course, which is the value of the integer. And similar, if you have a symbol string, then we have the tag that it is a string, and then we have also the string, of course. So that is this A. Then we have the rewrite rules. And then this is also important, we have a set of Terminator symbols. So you must, when you have a start symbol, you need to tell what comes after that, what terminates the input. And I call this the Terminator symbols. So this is typically an end of file or maybe a semicolon or a dot, whatever you want to terminate input with. Okay. And then a token, this is a bit weird definition, is a tag together with an attribute that agrees with this A function. This is of the correct type. So, yes. So here is here is a very simple example. I just took an outline of a strong simplification of the C language. So a statement can be a while parenthesis expression, closing parenthesis, another statement. So you could have another while here or an if or whatever. A statement can be do statement while. It's really very much simplified. Or with a condition, it can be if an expression then a statement, if expression else statement. And for can have two statements, right? You can omit one of them. I think the first one. And you can. This shouldn't be here, this parenthesis. Something went wrong here. So a for has three statements instead, and not this. Okay. Now. Okay. Okay. So now I'm going to show this in real. The time is okay. I see it. It should be okay. So this is a standard example. I'm going to show the parser generator. This is a standard example which comes from Yak, I think, and Cap also uses it. So I'm going to show you a calculator that takes priorities into account. So this has got priority over this one, and it can also store variables. So you can say A becomes 1 to 1, and then later it remembers that A has this value of 2. So is that really, so 2 minus 8 is really minus 6. And the operators are standard, but there are priorities. So, yes, I have to think a little bit. So first attempt to write this grammar would be possibly this. So you say A goes to A plus, expression E goes to E plus E, E minus E, E times E, E divided by E. Or double identifier or between parentheses. So, but this is of course not good. What is the problem with it? Yes, it doesn't specify the precedence between the operators. It's obviously not a good choice. Right, if you have, say, double plus double times double, you can say A goes to E plus E, and then this E goes to E times E, or you first do E times E, and then this one goes to plus E. Then the string has this has different meanings. So that doesn't work. And that's called ambiguity. It is very bad. We don't want that. Because then the meaning is not well defined. So we're going to do it different. So what you do, the standard solution is to introduce different levels of, so this E just becomes different letters for the different priorities, for the different precedences. Okay, so this F, for example, cannot contain a plus anymore because it's lower. And because of this, the first one always must have the priority. And also here, this F and G, they don't contain plus anymore. So this means that the plus is always on the top level. So which then means that these ones have the priority, the precedence. Yes. So, and okay, so this is the definition that works. And this has no problems with precedences. It gets the precedences right. So I show this now in the syntax of my system. So, yeah. So one of the so as I gave the advantage of my system that it's Maphoon, that it uses that you can use constructors and destructors, and that it does the memory management automatically. But of course, since all the attribute here is always double, you're not going to see that. Oh wait, it's not true. You will see it. Okay, this one has as an attribute. This is so right. If you write, say, f of something 1,2, say power 1,2. Then this 1,2 is an A, which is a sequence of expressions, and this is represented by a vector. And this has storage invariants. They will be respected. So I will show you now. So what I'm basically going to show you this in the syntax of my system, and you will see that it's equal to the formalism. Okay. So you declare symbols with this how to call it what's called % sign. And so some symbols have an attribute type, and you just declare it between curly brackets. So scan identifier and scan error have a string attribute. All these things, double of course has a double attribute, and this is this argument sequence. So this is a sequence of arguments of a function. It's a sequence. It's a vector of doubles. Yeah, and here can be anything as complicated as you want. There's no. You can have anything here. And here I have your more. So this yes. Yeah, so coming back to this definition on the slide 26, we have now this contains everything. This contains 26. Where is 26? Yeah. So sigma we have defined. This A was defined by the declarations of between these curly brackets. The rewrite rules we didn't define yet. Start symbol I mentioned, and I mentioned the terminators. So, okay, we should say a bit what we have to offer. So, okay. Okay. Yeah, I think I'm going to shorten a little bit. I wanted to tell that in principle there are two directions of parsing. You can do it bottom up and top down. And but since I'm a bit short on time and anyway not using it, I will skip the top down parsing. But I will say maybe 1 minute. So top down means that you start with a start symbol and that you rewrite it down to the string that you actually have. So and that you apply the rewrite rules from left to right. So right, if you have let's go one by go. So you know what you need. So you know that you need a start symbol, and then you need to decide if you have this rule or this rule at hand. So you look at the start of your input, and then you choose the one. And for example, if you know that you need to recognize an E, then you look at your symbol and decide which rules you have to start. But so top-down parsing has the problem that you look at your first symbol, you know what you need, but you don't know which rule you need to apply. Right, so if you need an E, But all of these e's, these e's and this f, they in the end start with a parenthesis or a double or an identifier, and you cannot choose between these rules. And this is the big problem of top-down parsing, is that you have to change your grammar. You need trickery. You actually need to merge these initial parts until the part where you have the information to choose. So there exist top-down parser generators. How is it called? Antler. But it cannot deal in full generality with grammars. You always have to, in order to make it suitable for top-down parsing, you need to modify the grammar. So this is what I want to tell. So I go to bottom-up parsing immediately. Bottom-up parsing. So we are here. So this is a short and even shorter discussion of top-down parsing. So bottom-up parsing. So with bottom-up parsing we do it different. We look at the input word and we apply the rules from right to left. Well, and as far as I know, bottom-up parsing is necessarily shift-reduce parsing. Okay. So this is the parsing algorithm. So you have a chain of an input stream of tokens, and the parser sees only the first. So the parser can read the first symbol token, and that's called the look ahead. So this look ahead is actually is it written there, an optional symbol. So the look ahead can be there or can be not there. So if the look ahead is not there, the parser can ask the tokenizer for a look ahead, and so that it can be done where there is no look ahead, and then after that there is a look ahead if everything goes well. Well, even if not everything goes well, there will be a look ahead because there will be an error token. So it's guaranteed to succeed, but it could succeed with an error token. So then we have a look ahead. Now with this look ahead, we can. With the look ahead, we can decide to push it onto the stack. So we push the current look ahead into the stack, and then after that the look ahead is undefined because it was moved. This is the main. We can ignore the look ahead. We can look at the top of our stack, and if we have a complete right side of a rule on our stack, we can replace it by the left side of the rule, and that's called reduction or reduce. So this is shift-reduce parsing. We either shift the token onto the stack, push the token onto the stack, or we reduce the right-hand side of a rule. Yeah, and then this is finished if our look ahead is a terminator, and the top and the stack contains only a start symbol. That's the end of it. Yes. So. Yeah, and so the nice thing of the shift-reduce parsing is that it's very easy to compute the attributes. And I use the syntax of my system. So this is the rule E goes to E plus F, which eventually will be applied from right to left. So assuming that you know the attribute of this one and the attribute of this one, then the attribute of this one is of course supposed to be the sum of them. So you write this, just return E plus F. So this column little variables means that you give a name to the attribute of this one. So the YAC originally uses something with dollar signs. So I think this would be $1, $3, and then you have to write $$ equals $1 plus $2. But I like the cup syntax more. Moreover, returning stresses that it is an initialization. That's important. C++, of course, strictly distinguishes between assignment and initialization. And this is always an initialization. So I think returning is okay. No, the minus. And in this case, this rule exists only because of the operator precedences. You just copy the, how do you call it? The attribute. And this code is usually called action code. And it must return the type of the left side of the rule. And if it is not void. Some more examples of action code. Which slide am I actually? 40. It should be okay. So this is code where the variable is looked up. So if you have an identifier, The memory is just it's maybe not the right name, but it's just the storage of the variables. So if this variable contains this identifier, then you return the lookup. Actually, I don't like the interface of this; it should be improved. But then you return the value that is associated to it. And if it has no value, then you put it in the error log, and the user will eventually see this error log. Okay. Okay, it's very important. This error log does not contain syntax errors. It contains only semantic errors, because syntax errors, they are separate. And so even if you need still to return something. But you store a message that the user tried to look up an undefined variable. Okay, so. So here is something where a function is applied. So you have an identifier representing the function, left parenthesis, then the attributes in a vector. This is ours, and then you can do it. It's very incomplete, by the way. It's not. So you look up if the function is a sign, and then if there is one argument, you can apply the sign on this argument. But it's an example where vector is used as attribute type. Okay. Yes. Let's skip the rest and let's just show you some of it. Let's show this in action. That's nicer, I think. Make. So. So I set debugging on. Okay, so now the debugging is on. So we have a session. And this comes from the rule because we have session rewrites into lambda, into epsilon, so we immediately have a session on the stack. So let's evaluate expression 1 plus 2 times 3. So if I type a 1, yes, you see that this 1 has been shifted as an H. That's the grammar had its levels E, F, G, H, and now it's a 1. So if I now type plus, then this H will be reduced all the way up to E, because the rule is E plus F, and so the only way that you can do something with this H is by shifting it up. So I type the plus, yeah, and then you see this whole sequence of reductions G, F, E, A, and now we have E plus. Plus has no attribute. So I type. I don't remember what number I said. It doesn't matter. 3. 3 is again an 8. So if I now type a plus, I think this one will go all the way up to what will actually happen. This will become an EF, and that will be evaluated. So if I now type plus, this will go up to F, then it will evaluate this one, will have a single E. But if I type times, it cannot do this. And what will it become? I think it will stay an F then. We will see. So this is not. Yes. So now I can type something else, say 4. See, this is being shifted. So it's being shifted again. And now if I type the semicolon, that's the terminator, it will reduce the whole thing into the start symbol and calculate the value. Did it do this? It's hard to say. It is. Yeah, I will move on. The time is a bit shorter than I expected. I have to say what I wanted to decide now. Yeah, you can see it got evaluated, and it printed also the result here, and it will in session again. Yes, so yeah, we can do some other examples. If I say A equals 4, so we have to identify, assign, double. This was all the way. It went through the sequence of the reductions up to the semicolon. Then, while this rule was being reduced, it made the assignment, and now we're back in session. So we can also type the A, right? So this identifier, yeah, the rule was H goes to identifier, and when it reduces this rule, it looks up the identifier. Yes.
Your grammar has optional else, correct? You have an optional else on the if.
Well, the language has no if here, but yes.
Did your language not have if?
Yeah, but that was the C example, right? No, this is not a. It doesn't. This is another.
Okay.
Yes. But you want to ask about the ambiguity of that?
Well, that would be the classic shift-reduce conflict.
Yes.
You
Okay.
do a shift.
Yeah, I will now go to the conflicts. Yes.
Versus diff.
I will just go to the shift-reduce conflicts. Yes, that's true. So let's speed up a little bit. Yeah, maybe I skip the theory, but so of course the hard part is to the reduce to solve between the shift and the reduce. I wanted to say something about the theory, but I think I better skip this. There is this great book which explains this nicely, and the Dragon book, and it is in there. So we skip that. So. Okay, this is unimportant. So this is also unimportant. So adding preconditions. Okay, so you have shift-reduce conflict. You mentioned, and I have some language, some systems solve this by priorities, but I do it in another way. I attach conditions to the rules. So they're similar to the action code. So you add a function to it, which returns a boolean, and this boolean decides if the reduction takes place. So in the case of if then else, you have two rules. You have if condition then statement and nothing, or you have if then else. And so the first rule can be only applied then if the look ahead is not else. And you would put this in such a condition. So, but the example that I wanted to show is Prolog language. Okay, now let's, there's something missing here. So, okay. So in Prolog you can define operators. This is a nice thing of Prolog. So you have this op predicate, and so you can define additional operators. And once they are there, they are operators. So you mean plus, minus, define, but you can define logical end or whatever. So if you want to model such a language, if you want to do such a language with an automatic parser generator, then of course, you're in the trouble because you cannot change the grammar while the parser is running. And since I wanted to parse Prolog also, I added the facility that you can add preconditions to rules. And so it looks like this. So a precondition is similar to action code. It can, in a const fashion, see the attributes of the right-hand side of the rule. It can see the look ahead. And if there are any additional fields, global variables, it can see them. And it must return bool. And it returns true then if the reduction can happen. And of course, this must be const because otherwise the precondition could change the state of the parser and then refuse it. That would of course be terrible. So it must be const. And that's enforced by the compiler. Okay. Yeah, I will quickly show you some. So an identifier so if I write, suppose I write in Prolog A, B, it could be that this A is actually a prefix operator applied on B. And it could be also that B is a postfix operator applied on A. Right, this is Prolog. And what you actually need is you need a grammar rule prefix here, divides into operator. But this rule is only applicable if this identifier is actually was defined as an operator before. So it has this in the action code. It has this additional requires. But this requires checks that this it actually occurs in the store of the defined operators, and it also checks at the look ahead if the look ahead actually can start a term. So Prolog is very nasty grammar. So if you type A of B, and A is a prefix operator, then it's A applied on B. But if I would type A dot, then A can be not a prefix operator because the dot is the terminator. So this is why this extra check is necessary. So we look at the head and we decide if it could actually start a term. And if that is the case, we can reduce it into, by looking it up into an operator. So this is the syntax for it. I mean, I think I will not go through the details, but so you can add you can put a require clause to the rules, and this must evaluate to true, and otherwise the reduction is not applied. I will skip this slide. You also have at runtime to deal with the priority. So if you have, let's look at this one. So you have to look at the look ahead and to see if the look ahead is also an operator that has priority over this one, then you must not make this reduction. So, and this can reduce, it just looks at the look ahead, checks if it happens to be an operator that has a higher priority. And if yes, then it returns true, and if not, then not. Yeah. And then if you can make the reduction, then it constructs the tree here. This constructs the tree. Yes. So this just constructs the tree. So this string is transferred into a function and applied on the arguments, the T1 and the T2, and it is a tree. Oh yeah, by the way, this is this new is it goes straight into a smart pointer. Right, because the attribute of this in Prolog is defined as a term which is defined as a smart pointer to some overloaded classes. So we don't deal with the pointers. It gets cast by the compiler into a smart pointer. There are no naked pointers here. We don't want that. Okay. Yeah, I want to say yes.
Are all your operators left associative?
In Prolog, no, they can be right associative also.
Is that expressed inherently in the grammar, or it could also be expressed in terms of reduction?
Yeah, this can reduce looks at the priority and also at associativity. I mean, there's no time. Sorry. The question is: Are all the operators left associative? And the answer is no. No, they can be defined left associative, right associative, and also non-associative. And this can reduce predicate deals with that. And I didn't show the can reduce predicate. Yeah, are there more questions, or shall I go to the end? By the way, because. But is this? I think here is just another example of the same. So once you have this, somehow you see applicabilities of it everywhere. So sometimes you have keywords like that only make sense at certain positions. So if you let the tokenizer deal with these keywords, then they will be recognized everywhere. But since we now have this conditional reduction, so we can also let the grammar deal with the keywords. Yeah, and this comes from a Turing machine simulator. So a Turing machine, you have L left, stationary, right. But the same letters can be also identifiers at other positions, and at the other positions you don't want to transform the L into a -1. But by having a grammar rule, this grammar rule will be considered only at places where you actually could have a left-right stat, and so you can be certain that never accidentally an L will be transformed into a left-right state at places where you don't want it. So then it goes to a character on the condition that this character is left, stationary, right. And then the reduction is done here. So you look it up, and then L becomes -1, right becomes 1, and stationary stays 0. Okay. And here I think we really go beyond Jack and Bison. I think they don't have this. So this allows to. I mean, it's sometimes more convenient, but it also allows languages that change themselves while they are running, and especially Prolog has this. There may be other examples, but I'm not aware of any. But Prolog has this, and I wanted to deal with Prolog. It has been tested. So now, one final thing about errors, but I have not too much time. So shift-reduce parsing is traditionally bad at error handling. But actually not completely. So first of all, it's always possible to able to accurately report the position of the error. That's a big plus. So it's not that bad. It's also quite good at recovery, which you do by specifying synchronization points. But it's not good at giving meaningful feedback. And but maybe I solved this problem. So I will show you in 5 minutes how. I think I will skip recovery because this I just copied from Yak. It was okay in Yak, and I like it. So what should one say to the user here? Here are some syntax errors. What should one tell to the user? Just look a little bit about this and think what you would say. Okay, so So the general schedule that I use is as follows. So you have an expectation and you have a look ahead. And both of them are optional. So if you have no expectation and you have no look ahead, then you just say syntax error. So if you have no expectation but you see the look ahead, then you say unexpected look ahead, whatever it is. So if you have an expectation but you don't know the look ahead, then you say I expected the expectation. And if you have both of them, you say expected my expectation instead of look ahead. Right? So look ahead, we know how to get it, but how do we get the expectations? So and by this I use some kind of, I specify some kind of weak form of regular expressions. But let's, I have 5 minutes left. And I show it in code because it's an empirical process. So the idea is as follows. I think we're done with this. We have 4 minutes, okay. So debug. Let's create an error. So I say, let's say 1. Okay. This is what we said. So I think this is a reasonable error message, right? Let's do something like this. Let's do something terrible. A plus 2, 2. No, wait, we must recover first. Plus 2, 2. Okay. Yeah, it is. I'm not sure if we are recovered now. So 1. Let's check are we recovered. So let's do something like this. Right, this is a nice error. So if you want to specify something more, you have to define what you expect. And I do this by looking at the parse stack. Where's the parse stack? I don't see it. You have ident L, and so what I do is I add a rule. If you see ident and lpar, then you can define what you expect, and what you expect is actually a function argument. So let me quickly show this in. So we add to the grammar ambiguous. We add an error. Definitely, we say errors. Errors. And now I forgot if we have identifier. And lpar, then we say we expected a function argument. And you have to specify these rules just empirically. You have to generate the error. You look on the stack what you see there, and then you try to find something that triggers your expectation. I think it's ident and not identifier. Okay, then I quickly draw so bash math. I hope it will go. It's a bit slow. So, and now it should say something like, you see now it says expected a function argument instead of comma. So what you should do is you should generate the errors, look at the parse stack, and try to to characterize what triggers your expectation and put this in these rules. And and then you can give reasonable error messages. And one has to see how this holds up in a real application with real users. But I believe that this improves greatly the error handling of bottom-up parsing. So we move to my conclusion slide, because I understand we're a bit short. My conclusion. Okay. What do I tell? So this tool at least fulfills my own needs. I hope it will fulfill the needs of some other people too. Okay, this is important. Theory is great. It's nice to implement it, and it can solve your problems. But you have to be flexible. I mean, if there is something that your user cannot do, I mean, you don't have to do it for him, but you must allow the possibility that he still does it by himself. I mean, if there is something that your tool cannot do, then your user will just not be a user, right? Then so the target group for the toolbox, there is no excuse for anyone, I think, because it's so nice that I don't think there's an excuse of not using it. And the parser generating, I would say experimental languages teaching, I wouldn't use it in, say, in C++ because it has too much momentum. And and you can download the thing from this site, but it's a bit, I have a newer version on my computer. I have been using it, and students have been complaining, and I took into account their complaints. And then I want to thank a lot of people. So, I want to thank the following people complained a lot, and it was unpleasant when they did it, but I think in the end it was good that they did it. And this is sponsored by a grant from another Bayeux University. And I have 10 seconds left, but I think I will not use them, so thank you.